Yeah, well, thanks for the introduction. We were going to introduce ourselves a bit on this slide, so you helped us out.
Do a better job.
Yeah, yeah. We do feel that our background coming into AI safety, trying to understand models so we can understand the trajectory of where things are going, how we can make better decisions, how we can kind of create a more coherent science so that our efforts can be maybe playing off of each other and helping each other out a bit. So we're pretty optimistic about that. In physics, I've worked on a lot of things from kind of quantum foundations, quantum information, non-equilibrium thermodynamics, and I think what's most pertinent to pivoting into this line of work is asking the question of what does it mean to predict the future as well as possible in a very general sense. And now that we're training machines to predict future tokens for past as well as possible, that theory ends up being very relevant, which we're adapting, and we'll tell you about today. And teaming up with Adam has been great, coming from a computational neuroscience background. You want to say a bit about yourself?
Yeah, so like Ben mentioned, my background is in basic research in neuroscience, both computational and experimental. I focused on kind of a wide gamut of things, but that includes the computational properties of single neurons and how they perform their input-output functions in terms of their biophysics, all the way up to more kind of systems neuroscience, which was studying kind of how the cortex instantiates world models and affects sensory processing in rats. So one of the things that we like to think about in kind of our motivations for Simplex is kind of how science works and some of that kind of meta stuff. So there's this popular neuroscience paper from Eric Jonas and Conrad Cording from a few years back called Could a Neuroscientist Understand a Microprocessor? And what they do in this paper is they apply all the standard techniques of systems neuroscience, many of which, by the way, look very, very similar to mech-interp approaches today. And they apply it to a microprocessor that is running Atari games and seeing if they can kind of understand, using these techniques, how this microprocessor works. And their conclusion is negative. And they say, there is a popular belief in neuroscience that we are primarily data limited. Current approaches reveal an interesting structure in the data, but do not meaningfully describe the hierarchy of information processing and may fall short of producing meaningful understanding of neural systems, regardless of the amount of data. So a bunch of things could be missing from the approach. And one of the things we think about is the role of kind of theoretical frameworks to kind of undergird our thinking and our approach to science. So kind of scientific work without a framework kind of might have a bunch of these properties. You might have a kind of ever-expanding list of empirical results, and it's hard to kind of place those results in relation to each other and kind of connect them. You might have context-sensitive results where you're not sure to what extent the results even generalize, what lessons you should take to it, does it apply to other situations or not? There might be many unspoken intuitions, and a lot of the conceptual tools will be hand-wavy. So this might look like something like, I don't know, talking about world models, and if transformers can have a world model, and then there's like kind of endless debate if they're just stochastic pairs and world models, and it kind of feels like no one really has a handle on what these words mean, but still these concepts seem very important. And like I just said, discourse might feel circular and repetitive. People might be talking past each other. And finally, there might be limited ability to control and monitor your system because you haven't kind of cut up nature correctly at the joints. And so you don't even kind of know on which dimensions and how you should manipulate the system and monitor the system to understand and control it. And we should say that kind of this is not to disparage any field. In some sense, the entire point of science is to work through this necessary process in order to make a framework to kind of get past these things and move on to the next kind of science. But it is important, we think, to kind of keep this in mind, and this being the goal, to kind of create one of these frameworks that can really kind of bridge the gap between mechanism and behavior and serve as an undergirding for our understanding of these systems. And so what we've started to do is kind of take a step back and ask kind of pretty fundamental questions. Like, what is the relationship between the structure of the training data that we bring to these systems, the internal structure of the algorithms and the computation inside of these neural networks, and the structure of their behavior? What does this word structure even mean? How do we operationalize it? How do we relate these things? So hopefully we'll give you a little bit of a taste and convince you that we're kind of on the path there. We're not saying that we have all the answers, but we have like a certain framing that I'll tell you a little bit about. Sure.
Yeah, so one solid foundation that we found really useful for starting off is adapting this framework called computational mechanics. And I guess I want to get through that this is really a useful foundation, but also not like the ultimate answer. But it's so far been working out kind of surprisingly well, just to adapt to the theory that's already been done, and then to say, okay, given the kind of unique scenario with neural nets, specific architectures, say, how would we have to adapt the theory to answer the questions that we're most confused about or that we most want to address? So what is this thing? Computational mechanics, comp mech. So it really comes from this history of physics. You can kind of think of it contextually that way. Physics is often tried to say, what does it mean to predict as well as possible? And then we'll have maybe our equations of motion, from celestial bodies to quantum mechanics. And we're kind of, in physics, often comfortable with the very ordered when you have, you iterate your ODEs. We're also, on the other hand, the very disordered. Maybe you have thermodynamic systems where you can talk about just the randomness of the system. We quantify that with the entropy, and of course that ends up being this kind of powerful thing where we can get material properties and so on. But what's the general scenario? Like, is there a middle ground between this complete order and complete randomness? That's kind of the task which computational mechanics addresses. What does it mean to predict as well as possible? And it turns out that it's not just like predicting deterministic stuff and sprinkling a little bit of randomness on, because randomness happens in different ways, that it can be completely ephemeral, or something that you didn't expect to happen can then embed itself and have impact on the future. And so studying what this is like in a very general sense has actually been surprisingly rewarding and given a lot of beautiful mathematical framework. So concretely, you could ask, okay, I want to predict the future from the past. What about the past do I need to hang on to predict the future as well as possible? So there's some kind of simple ideas that when you kind of make it mathematically formal, it's useful. So you look at those core screenings of paths that basically don't make a difference for the future. And that means that you have to store less stuff, right? Otherwise, there'd be an exponentially exploding number of things you'd have to hang on to if you're trying to remember more and more past. So formalizing some of these ideas takes us to something kind of intuitive about what's it like to store beliefs efficiently. It turns out there's some kind of computational structure, and then also what we'll get into a bit, there's a bit of a geometric structure implied by that.
And would you like questions during the talk or at the end?
I'd be happy for questions during.
Yeah.
The one clarifying question, this is actually for me as well. Is this an accurate restatement, which is if there was no structure, then the amount of information you would need to store in a system would just be overwhelming. And so it has to be made more compact in order to have this memory in order to predict future behaviors?
I wouldn't classify it exactly that way. Like if it's no structure, you think it's totally random, so I need to store everything. Actually, at that extreme, you need to store nothing, because if everything you see is IID, didn't depend on the past, then you wouldn't have to store anything. On the other hand, if it's very structured, not random, then you do need to store some things, but maybe it's a simple set of things that you store. And there's kind of this middle ground where kind of complexity emerges, where also agents are tasked with probably the most complicated prediction. So there's kind of the interesting middle ground, which is neither completely deterministic nor completely random. Yeah.
Also, who I jump in with a question, sure. I guess. Yeah, I mean, I'm sure you'll tell us more, and I'm fascinated. But a couple of things that come up, at least in the human cognition world here, is so you can't store everything. You have to compress, and what you compress and how is it's sort of a choice that is goal dependent. Right. So I'm curious if you get into this, because it's not just about the amount of structure. It's actually what when you compress, what you consider noise, what you want to optimize for downstream. So I wonder if that's also something you're thinking about, because it is going to depend on the computational goals of the system.
Yeah, that is something that we're thinking about, and that we have a little bit of an angle at. I guess I'd say that in the broad way that I'm painting it right now, just to predict as well as possible, if you actually do that task as well as possible, then you'll build up a memory structure sufficient to achieve any goal at all. But that's also going to be, because you predict everything that's predictable. But maybe that's too big of a burden. And so it's like, well, all I care about is where I'm going to get food from. And so you ignore certain other aspects of things in the future. So goal directedness can help you to kind of course grain effectively the predictive states to ignore.
Yeah, because what you end up doing, right, is forming certain abstractions, right? And that's going to determine how you generalize. So in some sense, there's actually a specific benefit from compression. I mean, again, to the limit that, you cannot predict everything, so you have to choose, and then your choices will affect downstream tasks in what you consider the same thing, and therefore generalize.
Yeah, I appreciate your point. I think to the extent that I hear you right now, I agree with you that there's something, at least like an objective function, that would weigh like how much you care about certain things in the future happening, and how your compression happens. So I think that's an important direction forward for us also. We have some ideas about that, but we should chat more about it also.
Yeah, absolutely.
Yeah. Right. So let's just say that Comet comes out of a rich history, so we have a lot that we can borrow, but it's also helping us springboard to the future, and so we're adapting it as needed. Right. So then that takes us to kind of the current state of affairs with AI, where we're trying to understand these things. Like we train models at next token prediction, and then we argue about whether they're stochastic parrots or the range model and what it even means. What does it mean to be good at prediction? How does that correspond to understand it? So there's various ideas floating around. For example, there's this kind of famous quote by Ilya. Is going on saying predicting the next token well means that you understand the underlying reality that led to the creation of that token. So there's a lot packed into each of these things. Predicting the next token, we all know technically what that means. Understand, again, what is this? What's the underlying reality? But something about there's a world model. But kind of up until this point, there hasn't been a very good mathematical framework to like make this falsifiable or not. So in comes computational mechanics and kind of making things rigorous. Computational mechanics says, yes, actually, you're right, Ilya, that predicting the next token as well as possible, it does indeed imply that you should be able to predict the entire future as well as possible. That means that you will have to infer a generative world model, but it's also more than that. And the piece more than that is you also need some way to synchronize to the hidden state of the world, because you don't see everything all at once. So kind of as you move through context, models must learn some way to basically do Bayesian updating over the hidden state of the world. And that's an important difference. So just to give a simple example here, what if we had the model of the world, right? What if the world was like this thing on the left? It's just some 3-state hidden Markov model. Why hidden Markov model? Well, it's representative text being non-Markovian, that you don't get to just make the prediction based on the last token, right? These kind of hidden states matter. So you train a model on this, and what does, say, a transformer learn? Well, maybe pre-convec, you'd say, well, it learns that the thing has 3 states, and there's a transition probability. Well, no, actually, convex says it should actually learn something like this crazy fractal. Well, what is that? That's some natural geometric embedding of these optimal belief states. And even more than that, we were saying, yeah, somehow this should be in the residual stream. And so Adam did some beautiful experiments where you'll see training from left to right. This geometry of belief states is actually linearly embedded in the residual stream of transformers. And so we've worked this out from various toy models and come to understand this a lot better. But we take this as a very general lesson that we can build upon and say, hey, we actually have a better idea of what models are doing. This is one of those things that's helping us bridge this figure. So just to make it a little more clear what the heck that theme was, I'm gonna go through an example here where okay, what's a hidden Markov model like? Okay, you have some latent states here, S0, S1 star. This is a 0-1 random process. Pretty simple. The process would emit a 0 and 1 and then half on something else, and you just go around saying, there's some labeled transition matrices which give conditional probabilities of, if I'm in this state, what's the probability of both going to the next state and giving a symbol, say 0 on the top one, or going to the next state and giving the symbol 1. And then what does it do? It produces just a time series of correlated variables, well, instantiations of that, 0, 1, 0, 0, 1, so on. And well, we were saying that models are actually going to learn how to predict this thing. And so what's prediction like in this case? Well, you have these belief states, eta here, that would be like a probability distribution over the states of the model. And you don't get to see what that is, right? You see the output, but you don't directly see the states. And how would those be updated? This is basically just straightforward Bayesian updating with matrix multiplication. That's what you see on the block. Okay. And so you iterate this sort of thing. As you see symbols, you say, well, what's my new distribution of this, which has a direct correspondence to what's my belief about the future? And you go through that, and there's kind of this computational graph that you get. You get another hidden Markov model, but you have a start state up there from your initial state of ignorance. Even if you knew the process, you still have to synchronize it to CNS to in context. And then finally, in this case, you get to these recurrent states. But then it turns out that not only is there this kind of graphical structure, but I alluded to this already, there's also an implied geometry in terms of how these belief states embed themselves in a probability simplex, the probability simplex of the latent states. So there's some implied geometry here, the belief states, and there's also, not really shown, but there's an implied dynamic or kind of a meta dynamic of how your beliefs change as you observe through context. Right. So that's kind of a bit of a background, hopefully to ground a bit. And I'm going to tell you a little bit more about how we actually find this in that course.
Yep. So the basic experimental protocol we're going to use here to apply this to transformers is to train kind of transformers in their standard scan on sequences data generated from these Markov models. For every input, we'll have some residual stream activation that will be of the dimension of the residual stream. So at all context window positions and over all possible inputs, because these are simple toy models, we can literally just enumerate all of them, and we can get the activations in the residual stream for every single one. And then given a data generating process, we have a theoretical prediction for what the geometry associated with that belief updating process looks like. And then we can regress the activations, which are in these cases that we run here, in a higher dimensional space than the belief state geometry, and see what the best linear plane we can find inside of the residual stream, that when we project the residual stream to it, kind of gives us back that geometry. So here's what it actually looks like in experiment. So we have this very simple 3-state process that speaks in a vocabulary of just A's, B's, and C's. This looks very simple, but as stated before, the actual belief state geometry is highly non-trivial and fractal, which is why we use this example, because we want it to be like a good non-trivial test of theory. And then we go and we probe the residual stream, in this case in the last layer, before the final layer norm and unembedding for this fractal, and we seem to get it. It's pretty cool. We see it develop over training, and we run a number of cross validations and shuffles to control to make sure it's not kind of trivially bound. And I won't go through the details, but we do have a manuscript on archive that you can check out. And then we also apply this to another toy model. Importantly, these belief states are, in general, distinct belief states can have the same next token prediction. And so one way to think about the claim we're making here, and kind of one of the most interesting statements about this thing, is that even though these belief states have the same next token prediction, and even though we explicitly train a next token prediction, still we expect the transformer to represent and keep these distinctions in belief states distinct, which might intuitively sound weird, because like, why do you need to keep things distinct if they lead to literally the same loss, and loss is what's being propagated? Well, the reason is because intuitively, different belief states can lead to subsequent next belief states, which can then lead to differences in next token prediction. So this is kind of just another way of thinking of what Paul was saying about kind of next token prediction. In this case, implies prediction over the entire future. And so this is another process called the random XOR process that has 5 hidden states. And what this process does is, if you start from the middle state, then you generate 2 random point flips, and then you take the XOR of the previous 2, and then you start over again and you cycle. So coin flip, XOR of the previous 2, coin flip, XOR, and so on. There are 36, unlike the previous process where you had an infinite number of belief states in this fractal pattern. In this case, you get 36 distinct belief states in a 4D space, which obviously we can't visualize, so we just kind of look at it from 2 dimensions, and you get this kind of X-ray crystallography pattern. And importantly, many of these belief states have literally the same next token prediction. And yeah, we still get the experimental results of that regression that we described before are in C here. We still get these distinctions in belief states. It matches quite nicely to the theoretical prediction. And then what D is doing, and I won't go through the details, is just trying to see if the relative distances in the distinct belief states in C are better described by the distances in next token predictions, or distances in the actual belief state, belief states given by our theory. And for the random XOR process, the belief state distances kind of more or less perfectly match what we get. And the next token predictions actually do not explain the geometric structure that we find. And then another interesting thing, and another thing that our kind of theoretical framework can explain, and that, to be honest, we were not looking out to explain. This is like one of the cool things when you have a nice theoretical framework that you can kind of go past what you're even trying to look at, is in the case of the fractal in the MES3 process that we were showing before, what you find is that the fractal is there right before the unembedding in that last layer. This is not the case for this process. What you find is that you actually have to concatenate all the layers, all the activations from all the residual stream layers in order to get back this structure. But there's a theoretical reason. This actually makes complete sense when you think about it. The statement of computational mechanics that we get says that the distinctions between these distinct distinct belief states that give rise to the same next token predictions need to exist in the transformer, but it doesn't say where. And in particular, because what the unembedding does is go from activations to next token predictions. At that level in particular, you don't need to keep these distinctions alive. The distinctions are only there in order to lead to kind of in context next belief states, which then eventually can get read out by the unembedding. And so this gives a quite natural explanation for the differences that we get in where kind of in the layered structure of these transformers, we find these belief states actually represented. So just kind of in conclusion, we were able to make this very concrete and specific theoretical prediction about residual stream activations and their geometries given the kind of data generating structure, and then show that they hold true in experiments. This makes us feel good about the formalism we use to make these predictions. And kind of the more general statement is that this formalism helps us relate kind of arbitrary training data to internal geometric structures in LLMs. Conceptually, as Paul described, we take this to mean that LLMs implement an algorithm that allows them to synchronize to their internal world model. And this can all be formulated with computational mechanics. The way that you say it in computational mechanics is that LLMs represent the mixed state presentation of the data generating process. Again, just to emphasize this, the structure of synchronization is in general richer than the world model itself. So LLMs, we should be thinking of them as learning actually more than just the world model. And then kind of overall, this kind of sets the stage for us to use this framework to kind of attack other kind of outstanding issues in AI research and AI safety more generally. So kind of how are we doing on time?
Doing well. Got like 30 minutes.
Okay, perfect. So going forward, I want to talk about like kind of a bunch of the different ideas we have to actually use this framework and expand it and actually apply it to kind of AI safety research in various ways. And we have kind of three things that we want Simplex to do. One is stress testing our framework, right? We did this in very toy models with ergodic processes, and there are a bunch of different ways to scale up and see where our assumptions and where the kind of hyperparameters for our experiment, where they kind of break, and especially as we scale up to natural language, if and how they break will be very important. We want to, if we have a framework that really is general and works to think about the relationship between the structure of training data, LLM behavior, and model internals, then we should be able to create benchmarks for various AI safety techniques where they don't exist. So like, we'll see an example of this later, but just to highlight it right now, a lot of research is going into sparse autoencoders, and it's a little funny when you think of how much energy is being put into sparse autoencoders that there doesn't really yet exist a satisfying ground truth benchmark for them. So for instance, if we could create one using this framework, that'd be great. And then finally, we'd like to kind of create a science for AI cognitive capabilities. And we'll give some, so what we're going to do now is kind of go through and give you a taste of a bunch of different avenues that we want to explore many of them will touch on multiple points of this. This is not like our entire thinking of what we want to do, but just to give kind of flavors. Yeah.
Can I just ask a question about the prior part?
Yeah.
Yeah, thank you. Super, super fascinating. And I cannot pretend to fully understand the math. Certainly I'll try to read the paper, but to make it, I just want to check my understanding and then see if I can ask a question, bringing it into a really concrete domain. So this debate, so Ida's point, I think, is really interesting because I think it can't always be true. Like, it cannot be true as stated in all cases, because unless you have unconstrained amounts of data, a lot of the time just predicting the next thing will not give you the right generative model of the data. And I think that's often true in let's say, vision examples. And I think that's like a really good concrete case where if you're predicting at a pixel level, like what's going to happen in the next frame, you're not necessarily going to get a model of physics. So you, like, let's say you have like a rotating object, right? Like you might predict the next pixel, but you may never come up with, oh, the generative model, right, is like the rotation and the lighting and like all these actual things, right? So I think with unconstrained amounts of data, I think your point is sort of like eventually you'll get to a model of physics. Is that kind of right?
Yeah. So I think you hit on this part, right? Like a lot of what we were describing this first part was what must the model do if it minimizes loss? And in that case, to minimize loss in the next open prediction, it has to predict the entire future. And I think the limited data is an important point. And actually, one of the things that we're going to get to here is like, okay, next steps of CompMech and adapting CompMech actually helps us to understand what we expect the model to learn as it goes through training rather than just at the end when it's done very well. Because that's also a question of just like, we're impressed by models, but how well do they actually predict? Which is then another advantage of CompMech. It actually allows us to benchmark that. What does it mean to predict as well as possible? We know how far are we from that. Also, what we expect the role model to be at that point. And then I think there's this slightly different thing, which is not just how much data you have, but that's how small your memory is, which is really, I think, the driver for memory compression. Why, you maybe have some natural, some inductive biases with the architecture, but if you want to do as well as possible and you have constrained memory, then it makes a lot of sense to like develop physics. Then it's like, this is going to get you really far. All I need is a few of these equations. So I think there's an interesting interplay between limited data and the limited memory. And that's, I think we have an approach to both of those things and are excited to dig into that more and to interact more with other work and other approaches.
Yeah, I guess that definitely speaks to my point. And I think like, I guess what I feel like might be true, but I'm not sure if what your mathematical result is saying is different, is that like, basically you're not saying that you're definitely going to get a generative physics model out of training pixel prediction. Like it could be true, but it's not always true. And it's an empirical project to discover if it's true in a specific case. Is that right?
I think mostly yes. Yeah, I mean, there's, I guess in the mathematical results, there are some things that must be true, but there's also definitely some, a big empirical part of this that didn't have to be this way, it seems.
Because I think we don't know the empirical answer. Like, I guess I'm trying to bring it into the concrete case outside the math and try to link them, but like, concretely, it is not true that vision models come up with like deep nets of vision necessarily come up with a model of physics in practice.
Right. I guess another thing to say that's a little bit interesting to think about, and I do think this kind of issue is at the heart of our thinking and motivates a lot of, at least part of what we want to do in the future. But for any given finite data set, except for any given data set, but for the finite data sets that we work with in training these models, the hidden Markov model, that form that we kind of assumed, allows you to express that. The pixel-wise data that we give vision models, that hidden Markov model might not be one-to-one with the actual physics of the world, right?
That's right.
And so I'm not saying I have the answer to this or anything like that, but thinking about the relationship between those two things, even just kind of operationalizing into that, like kind of at least gives you a lever, hopefully, to attack and think about the relationship between those two things and what the implications are for these models and how that interplays with things like what Paul was saying with memory and resource constraints and stuff like that. Yeah.
Thank you.
Yeah. Would love to talk to you more about that later too. So, right. So moving forward, now that we do have both these kind of mathematical and empirical initial steps, one of the things that we're looking at is, okay, we've been able to say something non-trivial about internal representations. What are the implications for behavior? So I've mentioned already, well, okay, models are synchronizing to the role model. Synchronizing to the user has implications. We usually think of this in-context learning as, I'm not going to give straw man of how people think about it, but maybe it's a bit confusing. Whereas COMEC offers a concrete prediction of, yes, in-context learning should happen. We can predict timescales of in-context learning. So here's kind of a cartoon of what is the data like that we train on. It's not just coming from like a single HMM, of course, but the data we train on is very hierarchical in that you have different languages, different genres, different authors, different moods, right? So you can think about that as kind of disconnected ergodic components, perhaps, as a first brush. And what is it like to synchronize to the hidden state? So now not only do you need to synchronize to the hidden state of the model, you also need to figure out which ergodic component you're in. And in reality, we're tasking transplanners and more generally neural nets to do this, which means they're going to be learning in context. They're basically, their own entropy over their next token is going to be decreasing in context because of this non-ergodicity, generically according to a power law. And for a particular data generating structure, we can predict actually what this should look like. So for toy models, we can calculate this exactly. I'm showing this is again our random XOR process on the left that generates. On the right, that's an alternative representation of the belief state metadynamic. And there's 36 belief states that Adam talked about. And then the little graph that you see there bottom left is showing what I call the myopic entropy rate. It's the entropy of the next token as you look at increasingly long histories. So as you look at more context, as you scan through context, how does the entropy of the next token change? And so generically, that's going to be decreasing for these stationary processes to it would just be the Sharon entropy rate. And the way in which it does that, you can think of as synchronizing to the hidden state of the world, right? So actually, a lot of this turns out to be linear algebra on the belief state metadynamic. There's some math to dive into. This is not the time, but just to say that we have a handle on this and are looking forward to understanding the behaviorist side of things.
And then another thing that we're interested in doing, that I described before, this kind of hits on really all three of those things we want to do in the future, but kind of fundamentally what are features is another thing that we can hopefully start to deconfuse for us as a field. So because we have this kind of formal framework and this theoretical framework that we think is hopefully quite general, and we can instantiate toy models and scale them up in rigorous ways and understand for each of them kind of a ground truth computational structure or algorithmic structure that the transformer should be implementing, and the representations that one kind of in some sense must be representing in order to carry out the prediction task that we pre-train these models on. Hopefully this can serve as a grounding for kind of what even are features and benchmarks for what are SAEs finding. And this is not to say that we're not making the claim here that these belief states are kind of what the true feature should be. But given that the belief states are in some sense the structure of the algorithm that must be implemented in order to optimally do this prediction task, there should be some relationship there. And we have some ideas, but this is work that's just kind of starting up. Another thing that's kind of interesting and relates to other parts of interpretability going on is kind of mechanistic interpretability from a different view. So this is actual experimental results. So we train a transformer on some process that has a mixed state presentation geometry that looks like this fractal. So this is the ground truth. This is not from the transformer. When you train the transformer and we do this we try to look for this representation linearly in the residual stream. We find that it's very well represented. But now we can go in and we can redo that process at every layer, and not just at every layer, but in anything that's going into or out of the residual stream, which means that we can follow exactly how this belief state geometry is being built up step by step by the transformer in a visual way that's quite intuitive, but beyond that, hopefully kind of also gives us a handle to ask and understand quite fundamental questions about, like, kind of what are single attention heads doing? What's the most they can do? What are they contributing, and in what ways to this belief state geometry? And so just as like a taste of this, again, this is like real data. In this case, this is another one of these processes that speaks in a 3-token language, A, B's, and C's. In the embedding, you just find 3 points, one for each of the tokens. When that goes into attention, you get a triangle. The triangle gets added back in, and you can kind of sort of think of it as something analogous to a convolution here, where you're taking this pattern of a triangle and you're stamping it at each of these 3 locations in the embedding, and now you get 3 triangles. And then the MLP takes that and stretches it to kind of fit into this fractal pattern, and so on through the layers until you get to the final one. So this is kind of like, I think of it kind of as mechanistic interpretability, but from a slightly different point of view. But
good.
Yeah. And then another thing we can do is look at these structures through the different layers, through the different components, and also through training. And as Paul mentioned before, there's both theoretical work and experimental work to do here. But just to give a taste without really kind of going into any details, this is work that's just starting up. As we go down on the vertical axis, we're going through the layers of the transformer, and then as we go left to right, we're going through training.
Sure. So I think actually this gets a little bit to the question you were raising earlier of, as we're data limited, what do models learn? And this slide's just kind of to point at the fact that we're looking into this and that we have some avenue into this. So there was that myopic entropy curve that I showed before, which is the next token entropy as you look at longer contexts. That curve, which is now in red, actually is that's the lower bound for cross entropy. So when you've learned as well as possible, then you'll hit that. But for while you're learning, you're going to have some cross entropy above that on your train test data, and basically don't have the time to go into it now. But we have a developing story about how this curve should emerge, and basically how structure more generally emerges over time, like how higher orders of correlation are being learned by the model. And this, for one thing, it gives us different ways to look at what models are learning. Like maybe just a very simple thing, you can look at how you can have different curves for different context positions and how that's changing as you go through training. And we can look for different signatures there to understand in more detail what models are learning that we just didn't really think to look for before. So I think, again, it's kind of a general framework, even though we're still iterating on it. It's like, it's just opening up more and more avenues for self-consistency that we can say, okay, we do understand models or we don't understand models. And, we have some idea of emergent behaviors or not. Yeah,
another kind of taste of a different direction to go in. This is kind of in the realm of kind of a cognitive science of LLM capabilities. So when I think of kind of cognitive capabilities, probably this is because of my neuroscience background, I think oftentimes of things like abstraction and generalization, transfer learning, that kind of stuff. And so in my own head, at least, the framework that we've presented here gives us quite a good language to talk about these things and instantiate toy models, and then hopefully in those toy models of, let's say, abstraction or transfer, understand the the story that relates mechanism, the model internals to their behavior. And then we can kind of scale that up as much as we can and understand and study the behavior in large labels relative to that story. So here's one example of how a story might work. And this is not experimental data. This is kind of conceptual. And actually, I guess in this particular case, it is exactly the type of hypothesis one can come up with just by thinking through the theory and kind of, I'll pre-register it here before actually running any of the experiments. So what we're going to do here to study abstraction is we're going to instantiate this non-ergodic process, which has two ergodic components, each of them being kind of basically the 0-1 random process that we showed before, except we're going to replace the 0s and 1s with x's and y's in one, and a's and b's in the other. So this will either give you training data that is of the form 0-1 random with a's and b's, or 0-1 random with x's and y's. And of course, when we look at this, we notice right away that these two processes, these two components, share the same hidden structure, the same abstract structure, and just differ in kind of the vocabularies they speak. So quite naturally, we understand and we're able to abstract away from the specific examples. But then what would it mean for a transformer to be trained on this data and then abstract? This framework gives us both a hypothesis for what it would mean in terms of model internals and a hypothesis for what it would mean in terms of behavior. So in terms of behavior, what it would mean is that you would be able to test on a process that is, again, looks very much like the 0-1 random process, but now every time there's a 0, you replace it with 2 arrows and you split the probabilities there equally between A's and X's, and every time there's a 1 arrow, you split it equally between B's and Y's. And then this would be asking the transformer after training to mix together strings of A's, B's, X's, and Y's in order to optimally predict the future, even though during its training, it literally never saw A's, B's, X's, and Y's together in a single training example. What would that mean in terms of model internals? Well, for each of these components, we expect there to be a belief state geometry embedded in the residual stream. And we can look at kind of how they're embedded relative to each other. And so in the case where they're not able to do this held out abstraction task that I just described, the natural hypothesis is that these two geometries live in largely orthogonal subspaces. Whereas if you can abstract, these subspaces align. And what's going on is that the transformer is kind of confusing. It's like, in some sense, making an error. It's confusing the states associated with it's confusing A's with X's and B's with Y's. But this confusion is exactly what underlies abstraction. And then, of course, if it's still going to act optimally on the original task, it needs to keep the information for the distinctions between A's, B's, X's, and Y's in some other direction. But this is all kind of operationalized. We can actually run experiments on this, see in which cases you do get abstraction, in which cases you don't. And then we can go into larger models, potentially even kind of real models in language, and look for similar structures and seeing if the story holds there.
All right. So speaking of registering predictions, okay, we've talked about Karmek provides all these answers, but it also allows us to kind of ask questions for how to reformulate things that weren't obvious before. And a lot of times when we think about, maybe we're doing mech-interp or whatever it is, you're trying to answer specific questions that maybe about computational structures that you take for granted. But one of the things about, what does it mean to compress the past? Well, you can have some minimal hidden Markov models, but why should neural nets be limited to discrete computational structures? In fact, they're acting in essentially real value vector spaces. And what does it mean to compute in that space? maybe we don't even know what to look for. And so, so actually leveraging a little bit of my work on how quantum mechanics can allow you to simulate classical stochastic processes with less memory than classically otherwise possible, I realized that a lot of the quantum advantage you get has nothing to do with quantum mechanics. It has to do with real vectors. It has to do with basically continuity with real vector spaces rather than discrete computational states. I thought, wow, that's probably true. And I thought about that for a while. And then at some point I realized, like, this is almost certainly true, that actually transformers should learn these quantum and even post-quantum shortcuts to memory compression. So this is maybe one of our weirder bets, is that we think that actually models will be taking on some of these more esoteric compression techniques where there wouldn't even be a finite hidden Markov model to produce the data. And I think that should help also with understanding like visual models where there's more continuous symmetries. But that's all a lot of work to do. So then I just want to highlight real quick that it's been great engaging with the community at large on this. There's so many directions to go. We really want to collaborate. We want to funding, permitting, build the infrastructure at Simplex to make this happen. But already we've held a hackathon. Adam was really crucial in making this happen, put a lot of effort into this. And it was great. We had maybe something like 9 groups in the end that spent an extended weekend thinking about CompMech from their own angle, coding stuff up, writing up projects. And it was really useful. There were some things that we already knew we wanted to know, and there was some things we didn't even know that we wanted to know. And so, for example, here we at the top, this is basically in an RNN that the fractal structure is there. Also, we thought, yeah, actually, the results we have, it's actually this model agnostic thing. So it's true in transformers. We should find belief state geometry in the residual string of transformer, but kind of a nice thing, it should be architecture independent. And then when you look at a particular architecture, then you can back out more specifics. So Keenan and Pepper, for example, verified that indeed you get the belief state geometry in the current neural networks. There was also other nice work by Ari and Shu starting to get at abstraction generalization with various resource constraints. So this experience, I think, helped us to see that we're not so talent constrained, that there's so many directions that we believe in, that we think are important, and we're excited to have more community involvement. And whether that's within Simplex or outside, we're just we feel like this works, and we're excited to see it grow.
Yep.
So I guess that goes a bit towards grow towards what? What are we working towards? I think this isn't really a comprehensive list. It's kind of scattered a bit, but a few of the high level points is that I mentioned we have something like a model agnostic theory of learning and inference that can help us to understand, where is all of this going? Where do we expect AI to go? What should we be looking out for? I think it is important that it's architecture independent. We don't even necessarily know what the architectures are of frontier models. But then given an architecture, it allows us to basically look inside, discover world models and new interventions. And then bridging that mechanism and behavior, we're optimistic that this can allow us to anticipate, both theoretically and empirically in cases during training, when you'd have emergent behavior, for better or worse. And part of this that we mentioned at the beginning is that we really we think the community can benefit from using words carefully and precisely, so that we can actually talk to each other and not talk past each other. So there's papers written where they'll use words like features and then give like 3 or 5 candidate definitions, and then just use whichever one was most generous to us in hindsight. But that's not really how science usually works. And so it can be really useful to have falsifiable predictions. And so we're hopeful that really taking this framework seriously can help us to to have more coherent efforts that would enable AI safety. Very high level, trying to understand the trajectory of intelligence. I believe that understanding can enable better decision making. I feel like governance is really important. Interpretability is usually pretty far from that, but I think it's important that we gear towards that. So with that, thank you guys very much. Appreciate being here, and thanks for your questions.